said before, we will enter the lower layers of OPC UA. My name is Alexander Ziegler. I'm from Siemens, and I'm leading the OPC UA TSN subgroup. And we are focusing on how to integrate TSN and in future 5G and other wireless technology underneath of OPC UA sub in specifics. And yeah, let me just dive with you into the agenda, and I will show you today some context where we use OPC and QoS in, of course, in industrial networks. Then I will dive a little bit into the way how we integrate QoS into OPC UA and considering concrete physical layers like TSN and 5G. We will talk about how the configuration workflow will look like, and to get you an idea how the bootstrapping of QoS would look like. And we will have a short overview of the current activities around OPC and TSN. Okay, you might have seen that picture several times. So this is the landscape of our OPC applications. And of course, we will also see different areas where QoS plays a major role, such as reliable streaming for data in events for cloud-based or edge-based applications. Then, of course, we had cyclic process data exchange for the FLC use cases, C2C or controller to device. And of course, in future, we might look at, for example, mobile robot applications, which need ultra reliable, low latency communication among each other. And that is will run over 5G or VLAN, WLAN technologies, hopefully. Yeah. So the question now is, what was the design goal of our QoS integration? So we didn't want to expose too much of the details of an underlying network into our information model to make to keep the flexibility of OPC UA as much as possible. So we built a kind of abstraction layer which allows the machine and application builder just to request the needs of its application to the network. So we defined such QoS requirement parameters, which, for example, could be that an application would need 100 bytes of payload to be transferred from one device to another with a certain period and with a certain maximum latency. So this is the way how the application and machine builder would define its needs in our configuration model of OPC. And of course, to make that work in a dedicated environment, or specific environment, we would rely on device vendors and industrial network vendors, which of course also need some agreement how to implement and what kind of TSN features to be used inside such a converged industrial network. So we rely actually on the outcome of the 6802 TSN profile for industrial automation, which is currently in work. And this defines, as I said, the different elements of TSN. You might know that TSN is a kind of, let's say, toolbox providing different mechanisms to increase the reliability, latency of your network. Of course, improve latency, to be correct. And but to select the right ones, there's the need of kind of collection of mandatory items to be used in such a system. And of course, we would not only be the only ones as OPC inside such a converged network, we also would have concurrent applications running in the same network, talking not OPC, but other fieldbus or whatever languages which might need dedicated QoS requirements. And this should be fulfilled by such a converged network. So what's the benefit of such an abstraction layer? The benefit comes in place when a plant builder or an application builder decides to move its application to a different network technology, like a wireless network system. And then the benefit of our defined QoS requirement parameters would be that they wouldn't be would not need to be changed and simply can be mapped to the new capabilities provided by this system. You can imagine here a 5G or a WLAN system underneath. And it's becoming more challenging if you start to combine different network infrastructures to one big network, or different network physics to one big network. For example, you connect your local machine network via a user equipment, such a kind of router between a wired and a 5G network, to an 5G network. This again will be connected to an industrial backbone that might be connected to an industrial WLAN network, and you would like to achieve an end-to-end QoS over all those different physics. So this is actually the challenge we are facing. And this challenge means that we need protocols and mapping mechanisms defining how these QoS requirements, which are more or less generic for any kind of network physics, how these QoS requirements can be mapped to the dedicated network capabilities or mechanisms. And in some places, you even need to translate them from one physics to another. Of course, this is not the business of OPC UA, but I just want to mention that we might face here translation from Ethernet to 5G specific QoS mechanisms and maybe back again. So this is the challenge here. We need service interfaces defining those mappings, and we need signaling protocols allowing to have this end-to-end connectivity. And of course, the different deployment options I mentioned. So if you look at a layer 3 transport mapping option, then we see that there is already some activity in the IETF. They're talking about DETNet there. DETNet is deterministic networking and is used for layer 3 QoS in such a layer 3 network. And this is a standard currently driven, as I said, in the IETF. They are taught, they already have specifications for the data plane mechanisms to be used. And they currently talk about the way how the control layer might look like. So this is ongoing work. But this promises actually a good umbrella technology to combine these different physical layers we see here to one big network, and makes it easier to extend or to have the good scalability of such a system. So in smaller systems, you might say, okay, well, I'm not interested to keep the layer 3 here. I'm fine with the layer 2 communication only, which is typical for some field buses actually. So then the situation changes a little bit. So we do not have the layer 3 connectivity, of course, here. We need to rely on layer 2. And for that, the 5G standards define a kind of logical TSN switch around a 5G system to allow the 5G system to be treated as if it was a regular Ethernet switch in some limited way, of course, but this is the approach they follow here. And for industrial WLAN, there's still work going on, actually on both sides. And in industrial WLAN, you will find the 802.11be amendment, which is looking at the TSN aspects to be added to a WLAN system. So, and with that, we could, in theory, have a fully raw layer 2 connectivity over such a system as well. And of course, OPC UA will provide those mappings to a layer 2 system in our concept and drafting papers. So when it comes to the question, what actually can be configured inside OPC UA regarding QoS requirements, then we have actually two major classes. Well, not to mention best effort, this is already there. But if you look at QoS, there might be two major qualities of QoS. Let's say you have a priority-based QoS, which you might know from classical internet working, which is using the IP mechanisms there, so the differentiated service code points, which are part of the IP header, and telling the network which class of traffic it is looking at. And this allows a kind of classification of different data flows among each other. So you can imagine to have an urgent, a middle, low prioritized data flow, and the network is able to differentiate them and treat them accordingly. And of course, the guarantees you can get really depends on the network technology behind that and doesn't give you real guarantees. If it comes to guaranteed QoS, then you might need to define the bandwidth you would like to use for your data stream. You might need to define your bounded latency you need for time-critical communications, and a deadline model is also supported, for example, for synchronized control loop applications, where you have synchronized endpoints and applications synchronized to one common clock. Of course, this needs some effort. That means you need a kind of signaling that tells the network actually what you need from it, and to have the guarantee that you really get it. And the network itself needs to do some allocation in advance before you can start transmitting data. So this is the price you have to pay in that guaranteed QoS section. So we support both types of QoS classes. But if it comes to availability and reliability aspects, these are things we still have to cover in one of our follow-up versions of part 14 or part 22. Okay, so maybe some words to that. And you can see here that depending on which layer you are using, you might use IP-based or Ethernet-based mechanisms to fulfill the requested guarantees from the network. So if you take a look at the layered stack architecture, then you can see that we put the QoS requirements inside the communication layer of OPC UA-based technologies, which is currently defined in PubSub itself, and maybe used in future for client server as well, but this is not drafted yet. So this is something still open. So if you want to use QoS, you have to rely on PubSub communication mechanisms based on layer 3 UDP or Ethernet. And so underneath, we see the layers I mentioned before. And if you look at the different physics underneath, there we will find wired TSN, of course. Then 5G, as I said before, also has a notion of TSN, the mentioned logical TSN switch I showed you before. And Wi-Fi itself will also provide TSN mechanisms in future. So this is the layering concept we see here. And we, as I mentioned before, the service interfaces are important for us to be able to do the different kind of mappings to the layering, not only for the data plane mechanisms, but also for the control plane mechanisms such as signaling, reservation protocols, and so on. So, and when it comes to the question, what configuration mechanisms do we support currently? And I'll take a look on the TSN configuration models, which are drafted right now, and the mapping for that is drafted right now inside OPC UA QoS. So there you will have the two major approaches. One is the distributed configuration approach, which is using stream reservation protocols, which are running through the net from one talker to the listener and back through the network, hop by hop through the bridges and doing the reservation stuff. On the other hand, you have a centralized configuration approach with a centralized CUC collecting the QoS requirements from every publisher and subscriber, putting that together and request a stream from a centralized network controller, which rolls out the streams inside the network, and then the endpoint information, so the information for the endpoint stacks, will then be pushed back through the CUC to the publisher into the end station stack, so that the end station is able to know what destination MAC address to use, which VLAN ID, and so on. So these are the two approaches we follow, and we're hiding those different approaches behind this orange box called TSN control layer, which I will use as a placeholder in the next slides, where I want you to explain how the configuration workflow actually works. So as mentioned before, we have two end stations talking to each other. One is the publisher, one is the subscriber. Both have some QoS needs, which is the bandwidth or some latency requirements. And once the devices get connected to the network, then the TSN controller layer comes into place. This is then reading out the QoS requirements, the capabilities of the end nodes, the capabilities of the switches inside the network, doing some calculation, and is pushing back the information into the network and into the end nodes. And with that, you have established the end-to-end stream, and the process data can flow in a guaranteed way to its sink. That's the way, the generic way we have here for our dynamic configuration approach. And when it comes to failure situation, the TSN control layer is able to propagate diagnostic information here, for example, for a situation where the bandwidth there's no more enough bandwidth here in that port. This information can be pushed back to the end node and can be represented even in the OPC UA information model. So this is the purpose of the base network model. I will have some words on that maybe later. So diagnostics is also possible with that control layer and in our UA information model. When it comes to the usage of our concepts, you of course need to take a look at FLC, and FLC will of course use the defined concepts from PubSub and the base network model for the establishment of real-time communication flows. So FLC is just the layer above the QoS concept in the blue and the green area you see here. And what are the work items actually, or the outputs of our subgroup currently? We are contributing to part 14, where we defined a QoS requirement model for the application builder, as I said before, where you can define your QoS needs. We have a base network model where the TSN stream parameters can be defined and exposed to the information model of OPC. And you will also have some information about the network interfaces and their capabilities there. And finally, in a concept paper, we describe the different configuration workflows and have some usage examples how to use OPC QoS in general and make it work. And currently, the drafting and prototyping around OPC is starting. So of course, we have the OPC FLC working groups starting with creating a first release candidate for the C2C communication concept in general. They will start prototyping starting with C2C communication, and we have an OPC FLC TSN expert assessment group there, which is focusing on the needed data plane mechanism. It's special for OPC FLC. I mentioned that because in the blue part, we define the generic OPC UA mechanisms, and FLC is just one user of that basic QoS concept. There might be other applications in future, not OPC FLC based, which could make use of OPC UA. So the constraints which OPC FLC may need are a little bit stricter than that what is possible inside the OPC UA based technologies regarding TSN and QoS. So, and when it comes to the prototyping of the basic technologies, this is right now taking more speed. That means the prototyping subgroup will start soon, the prototyping the centralized and the distributed model concept for the configuration. And the base network model group will focus more on the future aspects of the parameters we might need in the network interfaces and streams. So for example, when it comes to redundancy mechanisms and so on, we need some more parameters here, and this is still work to be done. So my summary for that is that, well, FLC makes use of real-time safety and motion communication for factory and process industry, and that of course will need a framework which we provide in OPC UA to provide flexible QoS and the mappings to different communication physics and standards. And we see as an upcoming technology for the wireless communication physics, and of course DetNet as an umbrella layer for the end-to-end QoS, which allows us to connect various networks in a very hopefully simple way, and not to expose too much details of the network to the application. Then, as I mentioned, the TSN profile for industrial networks is an important building block for us, which gives us some guidance which features of TSN we might face and should support. And yeah, what really is important for our integration aspect is that the several physics, network physics provide a clean QoS service interface, which allows us to do the mapping. So that includes the signaling, the reservation protocols, and so on. This is what we need for the mapping here. So that's it for so far. And yeah, I took a little bit more time than expected, but maybe there's still time for questions and answers. Thank you.